All right, let's get started. So, hello, people listening in Zoom. Hopefully you can hear me fine. Also, this entire workshop will be recorded as well, so you can view it later. So this week we have a kind of special topic, and that's smart contracts. So this is the first time we've, like ACM Cyber has talked about anything related to this, at least to my knowledge. So I don't know, it should be pretty exciting. So the first thing I want to note is that this workshop is not going to be about blockchain specifically. I want to point out that distinction just in case people are more interested in that side of things. We'll take a decidedly less blockchain approach and just focus on the programmatic aspect of smart contracts. But even so, I want to just give a brief introduction to what blockchain is and why we should care about it in the context of smart contracts. So blockchains at its core, the core technology is actually not really related to financial transactions at all. Rather, it's more of just a method of obtaining decentralized consensus. And this consensus is basically the idea that a group of people all over the world can get together and decide on one common truth. And so there are a bunch of different protocols for getting that done. So I guess the first popular blockchain, which is Bitcoin, introduced this idea of proof of work. But you can substitute this proof of work protocol for a variety of techniques. So for example, Ethereum 2.0 uses something called proof of stake. That's fairly popular. And there are also a ton of fringe protocols like proof of space. That's proving you have a bunch of memory on your disks. Proof of burn, just a ton of different things. And that is also kind of irrelevant to what we're talking about today. But those protocols are what allows for blockchains to basically offer this kind of decentralized promise. Now, the next thing we need to talk about is the ledger. And so when we talk about what people come to a consensus on, it's the ledger. And the ledger is basically just a big chunk of data that's constantly growing. And so basically at every single time step, people are coming to a consensus of what to add on to the ledger. So every time we introduce a new block, people come to a consensus and decide to add it to this ledger. And in this sense, the ledger is append only because we can't change anything that was added in the past, or at least it's very hard to, but we can continue adding on stuff to this big ledger, so long as enough people agree on it. And so naturally, this applied itself to kind of eCash. Oh, hey, we just started, so you didn't really miss much. Yeah, so naturally, this was first transactions between multiple parties, and the ID transaction, I would say, here, I'm going to send 10 Bitcoin, that's a crazy amount, to Henry. And so if I publish this transaction and enough people in the protocol agree, yeah, this is valid, everyone basically decides to update the ledger to contain this new transaction that basically says, William submitted or sent 10 Bitcoin to Henry. And so whenever people look at that point in the blockchain, people can subtract 10 Bitcoin from my balance and also add 10 Bitcoin to Henry's balance. And so further on down the line, Henry can now send the 10 Bitcoin to another person. And that's kind of how blockchain facilitates a cash system. But the truth is, we can actually perform whatever kind of computation we want besides something as simple as eCash. And the idea is this, whenever I want to send 10 Bitcoin to Henry, there is some sort of logic being applied there, right? First of all, let's say the transaction is successful. The logic then would be, everyone needs to agree to subtract 10 Bitcoin from my wallet, which is just some arbitrary number, and also add 10 Bitcoin to Henry's wallet. So that's a piece of logic that typically you would have a program do. The other thing is let's say I don't have enough Bitcoin in my wallet, right? Let's say I only have 1 Bitcoin and I want to publish this transaction saying, I want to send 10 Bitcoins. Obviously this should be impossible because you can't have a negative balance. And so that's also another like piece of the logic in the Bitcoin protocol, right? You always have to verify that the sender has enough Bitcoins to send to the receiver. And so I highlight these two examples just to like make a point that even this eCash system consists of logic. It's just that the logic is actually just baked into the Bitcoin protocol itself. And the idea of smart contracts is kind of to like abstract this notion of like computation one layer up so that anyone can perform whatever type of logic they want when it comes to transactions. And that takes the form of smart contracts. So smart contracts are basically just custom programs that kind of can apply whatever logic you want. You can have a smart contract that just performs a simple transaction, like I said earlier. The smart contract basically will check that a sender's balance is more than whatever it's trying to send. If so, it proceeds with the transaction, subtracts 10 Bitcoin, adds 10 Bitcoin. But you can do something a bit more like sophisticated. You can say, I will only transfer money if it reaches like a certain threshold. Like you can only send at least 5 Bitcoin. If you try to send 4 Bitcoin, we don't allow it because it's like too worthless. And so by having people like just program this functionality directly onto the blockchain, you basically get like a ton of diversity in what the ecosystem can offer. And so how does this work specifically? The idea is that the actual program source code itself, or like a compiled form of it, is stored directly on the blockchain. And so whenever someone like tries to execute a transaction, everyone around them basically references that program that was stored on the blockchain and executes it and makes sure that like the logic all checks out. Now it's important to note that like since the blockchain is public, like the ledger is public, everyone has it. All of your program source code is also public. There's no such thing as like secret data in a smart contract because everything that you can see, everyone else can see. Furthermore, since transactions are also part of the ledger, like in this case, when we say transaction, we basically just abstracted this to interacting with the blockchain. Like if I want to buy something on this smart contract, that's performing a transaction if I want to like call that function. The point is that these transactions, just like how, like if I want to send money to Henry, that goes onto the blockchain. These transactions also go onto the blockchain. And so they're also public. And they're also irreversible, right? Because you can't change anything that happened in the past on the ledger. And finally, there's one thing to note. All of the executions of a smart contract are deterministic as opposed to like randomized. So like typically when you write a program on your computer, like if you're writing something in Python, you could do like import random and then random.randint something. And that would give you a random number. But that sort of thing doesn't really work on the blockchain because there's no true like source of randomness like in the world. It doesn't really make sense. And so because of that, all smart contract executions are deterministic, which could lead to like some vulnerabilities, but we'll continue on with talking about Ethereum, which is just a special type of smart contract ecosystem.
Okay, so Ethereum is a cryptocurrency that runs on a virtual machine. So the Ethereum virtual machine is called the distributed state machine. And this means that all nodes on the network have a copy of a single machine. And that's how they decide collectively how to make updates to this machine. So each of these nodes has smart contracts on them. And whenever you run a smart contract, you have to go to these nodes and make them all agree to update the state machine into a new valid state. And basically, the Ethereum virtual machine defines the rules for computing a new valid state. The machine is a single large data structure that stores all accounts and balances, and the machine state changes from block to block. So this is basically the graphic of how the Ethereum state updates. So in the middle, you have the y parentheses st equals s prime. And basically, this is just describing that the Ethereum state takes in the old state plus new transactions and uses those as inputs to compute a new state. So the state is stored as a Merkle-Patricia tree, which is kind of technical, so we're not going to get in too much detail with that. But basically, all I need to know is that all accounts are linked by hashes, and every single hash stored in the tree can be reduced to a single root hash. Also, fun fact, the Ethereum virtual machine is a stack machine with 1024 item depth, and each item is 256 bits long. And this is basically just to make it compatible with 256-bit cryptography.
Oh, also, let me interject something here. So like, just to give you like an example about this state transition, which kind of sounds complicated. So like, let's give an example in Bitcoin, for example. Let's say the old state is basically just a record of how much money I have and how much money Henry has. So if I have 10 Bitcoin and Henry has 0 Bitcoin, that constitutes the old state. The transaction that we're going to also feed into the state machine, in this case, is my request to send 10 Bitcoin to Henry. And so once we evaluate the transaction on the old state, we arrive at a new state, and the new state is just I have 0 Bitcoin and Henry has 10 Bitcoin. On the other hand, if like the old state was I have 5 Bitcoin and Henry has 0 Bitcoin, then this would be an invalid state like transition, right? Because I don't satisfy the requirements to actually perform the transaction. So this is all, that's all the state transition function really refers to. We can continue.
Okay, so transactions are all cryptographically signed by all accounts, which means that they have to agree to make the transaction. There are two types of transactions. There's a message call and contract creation. So contract creation basically just creates a new contract using the Solidity programming language and compiles it into bytecode. And message calls execute the compiled bytecode. So let's say if I have this contract that's written in Solidity and says, okay, transfer 5 Ethereum to this account. Contract creation would be just compiling that into bytecode, and a message call would actually execute the contract. Okay, so this is an example of the blockchain, which is typically used in Bitcoin. As you can see, like all the nodes in this network are basically just ledgers, right? They're just lists of every single transaction made ever, right? And compare that to the Ethereum virtual machine. And as you can see, it looks a lot like how a regular computer would run, right? You have the program and then you have the operations. And the program basically just updates the memory of the virtual machine. Okay, so now we're going to go into some examples of vulnerabilities. The first one is an integer overflow or underflow. And this is a vulnerability that's applicable to every program. So like just any exe file or something, if you have a variable where the user can input their own value, this is something you would have to check for. But this is especially dangerous in cryptocurrency since it's all numbers, right? So how this works is that each variable that stores a number is a fixed number of bytes, and if you go beyond or below the absolute limit of how much of what that variable can store, it'll overflow. So if you go above the limit, it'll go under, and if you go under the limit, it'll go over. So using this attack, an attacker can just enter a completely absurd amount of money to overflow the variable and completely drain an account. Okay, so reentrancy is another one. So smart contracts are all executed sequentially. That means they go line by line, right? So first you would request for withdrawal, then the crypto would be transferred, and then the balance updates. So if you've ever made a crypto transaction, you know that it takes quite a bit of time for everything to verify. So one thing that attackers realize is that, well, okay, if it takes time for the balance to actually update, what if I actually make another request before my balance updates? So instead, if I have like 5 Bitcoin in my wallet and I want to withdraw 5, then before that transaction completes, I keep withdrawing 5. And this makes it so that if this is actually a vulnerability on the system, then you could potentially drain multiple users' accounts at once, since you have multiple users like cryptocurrency being stored on the same block. So if you re-enter and then keep withdrawing, you're going to drain other users' Ethereum. Okay, and front running is another vulnerability. So the way that making a transaction works is that every transaction comes with a gas fee. And this is basically just a fee to incentivize crypto miners to actually pick up your transaction and process it. So higher gas fees basically mean a higher priority because there's a higher chance that crypto miners would pick up your transaction to process. So once a smart contract transaction starts, the key is public because the miners have to take it and update your account on the blockchain. So if you have someone else that's just waiting for an important transaction to start, and then basically just forks over a higher gas fee before the key is processed, then they can gain access to the contract before the actual owner does. And this makes it so that they can basically just steal the currency that's in the contract.
Okay, so that basically concludes the slides portion of our workshop. We'll also have like a demo afterwards about, well, like interaction with actual smart contracts. But I also just like want to summarize what we've talked about so far. So smart contracts are basically just like a system that allow for custom logic to be implemented on the blockchain instead of having the logic be baked into the protocol itself. And this, we guarantee the behavior of the program and its logic through decentralized consensus, just like in like a standard blockchain scheme. And the way that we interact with smart contracts is basically smart contracts expose a bunch of functions, like an API, and we can call these functions by performing transactions. The transactions is basically just like a word that we adopted from like eCash blockchains. And so smart contracts, you can view them basically as just like a bunch of programs that are all out on the web, right? And obviously when you code programs, you could like have bugs in them, right? Because no one's perfect. And what makes smart contracts particularly vulnerable, I don't want to say it's bad, but the point is just that all of the code is open source, right? All transactions are public, and they're also all irreversible. So like if someone were to actually like perform some sort of exploit and just take a bunch of money from like an account, there's no way to actually reverse the exploit because it was like a valid transaction. The smart contract accepted it. And since we have to follow the protocol, or at least the majority of people do, then you can't kind of like refund that other person who was stolen from, right? There's just no way around it. And so this is like good from a security perspective in that there's like a lot for us to do, but also bad for like normal people. Okay, and then just a couple of resources. So if you want to get into like smart contract hacking, there are a lot of kind of play competitions online, kind of like CTFs, but just specifically for smart contracts. So I want to highlight a few. One is Capture the Ether, which is what we're actually going to be looking at today. Another one, which is a bit harder and which kind of like delves into kind of the actual specifics of the Ethereum virtual machine, is called Damn Vulnerable DeFi. So that one is like a bit more high level. Capture the Ether is definitely good for like if you're just a beginner. And then also there's this researcher called Sam Sun, who's like super prolific in the community. He writes up blog posts about like just crazy vulnerabilities that he's found. So I'd also highly recommend like just going through his blog, just like inspiration. And then finally, Remix is basically kind of a web IDE for editing and compiling Solidity code, which is like what you use to program smart contracts. And we'll also be using that today. Okay, so let's turn to the demo. Okay. So, right. So we're going to be looking at Capture the Ether today. And if you're like watching on Zoom or here and you want to like follow along, like just go for it. All you need is really Chrome or any kind of browser that supports Chrome extensions. So the first thing that we want to do if we want to like play capture the ether is to create, and here are all of the challenges. So we're gonna like just go through maybe 1 or 2 challenges, and then you can also look at it on your own. And feel free to like ask for help on Discord later on if you get stuck. So the first thing that you need to do to actually like play a challenge is to install this Chrome extension called MetaMask. And so I'm going to, my password, okay, whatever. So MetaMask is basically a Chrome extension that allows you to interact with the Ethereum blockchain. And so once you've installed that, you can just create a MetaMask account. I kind of forgot what I made my password. Maybe it's like ACM Cyber. Oh, let's go. Okay. Okay, yeah. So if you make an account, it will kind of like look like this on the Chrome extension. And you'll notice that like right now I have 4 ETH. This is not real Ethereum. I do not have thousands of dollars just sitting in like an account password protected by ACM Cyber. This is the Ropsten test network. So there's the Ethereum mainnet, which is like where Ethereum is actually valuable and worth thousands of dollars. But we're going to be on the test network where basically all currency is worthless and you can just play around and send whatever you want. So make sure that when you like create a MetaMask account, you also switch over to the Ropsten test network, like in this drop-down menu here. The next thing you want to do is actually acquire some Ethereum, because whenever you try to send a transaction, you also need to pay a gas fee, just a small amount of Ethereum, so that miners are incentivized to perform your transaction. And so the way you do it in the Ropsten test network, if you want to get free Ethereum, is you go to a test faucet, and this faucet basically just like gives you free money. So you'll just like want to go here. It will ask to like connect your MetaMask account, I think. Yeah, so you can see here, my extension is connected to like whatever is running on this website here, and you can just request 1 Ether. Click this. It might take like a minute or so, but hopefully you should be able to get like just some play money into your account. So I have like 4 ETH. All right. The next thing that you want to do is get an Ethereum IDE. If you want to like work on it directly on your laptop, you have to install like the Solidity compiler and some other things. So the easiest thing to do is use this Remix application. And basically this implements everything like just on the website for you. Okay. So let's start off with the first challenge, which is called deploy a contract. So hopefully you've already installed MetaMask. You switch the Ropsten network, test network, and you've gotten Ether from the faucet. After this, this challenge is basically just to test whether your setup is working or not. So if I just like run the challenge, it will ask to deploy a contract. Now, as you recall, deploying a contract just means uploading it to the blockchain, which also costs a little bit of Ethereum. So we can like confirm, and it's going to start the process. You have to like wait a bit for like the miners to add it. This is taking a while. There we go. Okay. So the challenge contract has now been deployed onto the blockchain, whatever that means. But the point is, in these challenges, you want the function is complete to end up returning true. So when we do check solution, all that the server is going to do is it's going to call is complete, like send a transaction and call is complete. And if it does return true, then that means you solved the challenge, like whatever that means. In this case, the function just like always returns true. So like you win if you can just like deploy the contract. So now I'm going to check the transaction by performing a call. This again costs a bit of money. And hopefully that should just work. Yay. Okay, so we solved the challenge. Okay, so that was pretty easy, and that didn't really require any interaction on our part. So let's go to the next challenge, which is pretty simple as well. The idea is, so here, first of all, here's like the source code of the contract turn in Solidity. Even though it's a different language, you can kind of figure out what it's doing. So the first thing that it does is it has this global variable, which is going to be kept in this blockchain state, which is called is complete. And that's initialized to false. And so in order to make it true, we have to call this function. We have to send a transaction that calls this call me thing. It'll set is complete to true. And then when we tell the server to check the contract, it will be able to see that indeed, like you actually did call this function. So let's deploy this contract. And in the meantime, we're actually going to take this and plug it into Remix here. So what we're going to do is we're going to create like a new file. I called it callmetest.sol. And I just like pasted the source code here. And the point is like we want to compile the contract so that we can tell Remix how to perform the transaction, because it needs to follow like the API spec. Right. Okay, so the first thing we want to do is we want to compile this. So I just right click and then click compile. And there's a parser error. The source file requires different compiler version. So you can see here, like Capture the Ether is pretty old, so they're using an old version of the Solidity compiler. So we want to switch to whatever they're using, which is 0.4.21. And then let's try compiling again. And that works. Cool. Okay, so the next thing that we want to do is we actually want to perform this function call through a transaction. And we're just going to go here, the third icon, deploy and run transactions. And so that you first can specify the environment you want to run in. So this JavaScript VM just refers to like some local instance of the blockchain that doesn't have any effect on the actual Ropsten test network blockchain. So if you want to actually interact with the real one, you want to switch to injected Web3, and that will basically ask to connect you to MetaMask. So MetaMask is smart enough to they've all figured it out so that like everything is pretty seamless. You just select injected Web3, you should just enable the connection, and then now Remix will automatically perform transactions with your MetaMask account, which hopefully has money. And it's also automatically selected the account on MetaMask. So as you can see, that value matches, like this value matches this value, which is good. Gas limit, we can ignore, value we can ignore. And then we also need to select the contract. So in this case, it's callmetest.sol. And we don't want to deploy it because it's actually already been deployed by Capture the Ether to this address. So what we do is that we tell Remix, let's just like call it against the contract that's already loaded here at address. And now this basically gives us an interface for calling functions on the smart contract. So you can see there's two functions. One is called isComplete and one is call me. If I do isComplete, you'll see that the output is false because it hasn't been changed yet. And also, if we like try to check the solution right now, it should fail, right? And actually, MetaMask already tells us that it expects it to fail. The reason why it's able to do that is because it like simulated the entire transaction locally. But if you want to try anyways and send the transaction, something bad will happen. Also, if like you don't want to wait this long while you're testing your exploit, that's why you should just run it on like a local, like this JavaScript VM. But we're doing everything like directly on the Ropsten test chain, so it's going to take a while. Yeah, okay, so it says error, transaction has been reverted by the EVM. And that just implies that like the state transition wasn't successful. Your transaction didn't work with the old state to produce a new state. Now, let's now actually do is call me. Since there's like, it doesn't really accept any arguments, we can just like press the button. And let's just confirm the transaction. And you can also like view these things on Etherscan. Etherscan is just, or not yet because it hasn't been updated yet. But Etherscan is just a way for you to view contracts, transactions, just everything on the Ethereum blockchain. Cool, and then there we go. It's here. And then let's also just now check solution again. And then hopefully it should say we solved the challenge. You can also check is complete. You can see it changed to true. Yay, okay, so we solved the challenge. And so let's like just look at this one. This is like one that I actually haven't done yet on this account. This one is a smart contract that basically sets, is complete. It returns whether the balance, your balance is equal to 0. And the way that you can actually like change the balance is by calling this guess function. And in particular, this guess function requires you to like include 1 ether, like pay an ether. And if you guess the answer correctly, it will give you 2 ether. And so like if this was just like a program running on a server where you didn't have the source code, you obviously like this obviously would be a bad bet, right? Like let's say the number is between 1 and 100. If you just try to guess the number naively and you submit 1 ether, you're probably not going to get it back. So you just like wasted 1 ether. But if you can like get the number, then you've made a net profit of 1, right? Because 2 minus 1 is 1. But here's the thing, like again, as I mentioned during the slides, since all smart contracts are just living on the blockchain, they're all open source. And in particular, what it's comparing against is just like a static value on the blockchain, right? And so it's been hard coded here to be 42. And so if you just guess with 42, then you will always succeed. And so you kind of like will always win the game, the guessing game. And if we just like look here, there's just like a ton of other challenges similar to that, with just like increasing like levels of complexity. There are some other challenges just about different things related to Ethereum, but they're all fairly simple. Yeah, and the one other thing that you need to do, or you should do if you want to do capture the ether, is set your nickname. If you set your nickname, then you get to like show up on the scoreboard. So right now, I set my nickname to be DefundTest. And you can see a ton of people maxed out, but yeah. Okay, so I think we should just like call it here. Thanks everyone for like coming out. Again, if you have any questions related to like solving any of these challenges, just like post a message on the Discord or DM me at defund on the ACM Cyber Discord, and we can just like work through some of the challenges together.